In this presentation, we will be looking at X-ray diffraction in rare earth metals recycling. My name is Chineye Chinwego, a first-year PhD student in the Materials Science and Engineering program of Worcester Polytechnic Institute, and I'm currently working on rare earth metals recycling in the Energy Metals Research Group. So I'll start by introducing rare earth metals. Then I'll look at the importance of X-ray diffraction in rare earth metals recycling, and then go on to look at various works on rare earth metals recycling that had to make use of X-ray diffraction as a characterization process, and then I'll conclude. Rare earth metals are a set of 17 metallic elements, which include the 15 lanthanides, as well as scandium and yttrium on the periodic table. The demand for these metals in the past few decades has increased more rapidly than major metals like steel, aluminum, and nickel as a result of an increase in the demand for high-technology consumer products and clean energy development. The characteristic high melting points and high thermal conductivities that can be achieved with rare earth metals make them suitable for widespread use in high technology and energy efficient equipment. Also, the high maximum energy product value generated from rare earth magnets as compared to other permanent magnets make them suitable for applications that require high magnetic strength. They make good permanent magnets for electric and hybrid vehicles, wind turbines, are used as phosphorus for light bulbs and display screens. They have applications in chemical processing, glass polishing, and petroleum refining. We can find them in our computers and as steel additives in aerospace technology. In order to ensure security of supply and address the balance problem related to rare earth elements production, there is a need for the recycling of rare earth metals. X-ray diffraction is a technique for characterizing the arrangement of atoms in crystals and the distance between crystal faces in order to reveal detailed information about the chemical composition, crystallography, and microstructure of the material. In rare earth metals recycling, X-ray diffraction can be used to identify target elements or compounds and ascertain their state of chemical combination. It can also be used to identify phases present in the material both before and after recovery. Compared to other chemical analysis methods, X-ray diffraction is faster and requires small sample. Several researchers who have studied various processes and methods of recycling rare earths have made use of X-ray diffraction for characterization. A research work on the selective extraction of rare earth elements from neodymium iron boron scraps by molten chlorides was carried out. The neodymium iron boron scrap granules were mixed with the chloride compounds and heated. The extracted rare earth chlorides were processed with molten salt electrolysis to obtain magnesium neodymium-based alloy. In order to clarify the chlorination reaction of neodymium iron boron scrap in the molten magnesium 2 chloride potassium chloride mixture, X-ray diffraction measurements were carried out on the initial reactant and the obtained product after the experiment. Here, we see the X-ray diffraction patterns of the powdered scrap and the salts before and after the experiment at 1000 degrees Celsius for 3 hours. The X-ray diffraction pattern of the unreacted magnet crab was assigned as the tetragonal face of neodymium ion boron, as shown in curve A, and only diffraction peaks of pure ion were detected from the residual scrap after the experiment, as shown in curve B. This was in good agreement with the results of the EDS analysis. In this experiment, the mole ratio of magnesium 2 chloride to potassium chloride was 6:4, and the molten chloride mixture was crystallized to form the orthorhombic phase of potassium magnesium 3 chloride during cooling to room temperature. Meanwhile, diffraction peaks of hydrated potassium magnesium chloride were also detected as a result of the deliquescent property of magnesium chloride. This is seen in curve C. Besides potassium magnesium 3 chloride and hydrated potassium magnesium chloride, trivalent rare earth chlorides of neodymium 3 chloride, praseodymium 3 chloride, and dysprosium 3 chloride were found in the obtained salts, as shown in curve D. In addition, formation of neodymium 2 chloride was also found. A study on the recovery of rare earths from spent neodymium ion boron magnets of wind turbine was carried out. A pyrohydrometallurgical process was developed to recover neodymium, praseodymium, and dysprosium. First, the magnets were demagnetized in a muffle furnace at 583 Kelvin for 60 minutes. Then crushing and grinding of the material was done to less than 149 microns. After this, the material was roasted at 1273 Kelvin for 6 hours. Leaching of the material was carried out with hydrochloric acid and precipitation with oxalic acid. Furthermore, filtration, drying of the leach residue, and roasting were carried out to obtain the rare earth oxides. X-ray diffraction was used here to characterize the leach residues obtained at different time intervals. We can see the X-ray diffraction pattern of the spent magnet of wind turbine, and from the powder diffraction file, this matches the neodymium ion boron compound, as expected. In order to further confirm the complete oxidation of the magnet powder at 1123 Kelvin, the roasted sample was characterized, and the X-ray diffraction pattern revealed complete conversion of neodymium ion boron to neodymium 3 oxide and iron 3 oxide. The mixed rare earth oxalate, upon roasting, produced the mixed oxide of neodymium, praseodymium, and dysprosium. This conversion was confirmed by this X-ray diffraction analysis, and the residue of iron 3 oxide was also confirmed here. Furthermore, a closed-loop acid process was employed in extracting rare earths from neodymium ion boron magnets. Because of the acid waste solution discharge problem, this method was developed whereby the extraction was based on corroding the magnet with hydrochloric acid. The magnets were first crushed and ground, after which leaching was done with hydrochloric acid, then treatment with an ionic liquid to extract the iron 3 ions with ammonium chloride, and finally oxalic acid to precipitate out the rare earth metals. The hydrochloric acid can then be reused in subsequent extraction. The X-ray diffraction patterns shown here were compared with the simulated X-ray diffraction patterns for alpha iron 3 oxide and manganese 3 oxide type neodymium praseodymium oxide. We can see the pattern for the insoluble material after leaching, and this agrees with the alpha iron 3 oxide. Also, The precipitate after reacting with oxalic acid is shown to correspond with neodymium praseodymium oxide. Here, the extraction and recovery of rare earths from waste fluorescent powder using alkaline roasting leaching process was studied. The waste fluorescent powder for this experiment mainly contained red powder of yttrium europium oxide, green powder of cerium terbium oxide containing magnesium and aluminum, and blue powder of europium oxide containing barium, magnesium, and aluminium. We can see from the process flow chart the various steps taken to obtain the rare earth chlorides, including alkaline roasting done at 400 degrees Celsius, 700 degrees Celsius, and 850 degrees Celsius. Figure 3 shows the X-ray diffraction analysis of the roasted product at various temperatures. In Figure 3a, at the low temperature of 400 degrees Celsius, the characteristic peaks of 1 and 5 are associated with the formation of yttria and sodium yttrates from the decomposition of the red powder. In Figure 3b, the temperature rises to 700 degrees Celsius, and we can see that the green powder decomposes to give terbium 3,4 oxide, europium aluminate, and cerium oxide. When the temperature rises to 850 degrees Celsius in Figure 3c, diffraction peaks are associated with the formation of europium 3 oxide and magnesium oxide compounds. Roasting tests were conducted using mixed waste rare earth metal fluorescent powder with sodium hydroxide and different molar ratios of sodium oxide alumina from 1:1, 1.6:1, and 2.2:1 ratios respectively for 2 hours at 850 degrees Celsius. In Figure 6a, that is the case of 1:1 ratio, the roasting product mainly includes sodium aluminate, yttria, terbium 3,4 oxide, europium aluminate, and barium aluminate. In Figure 6b, where the ratio is 1.6:1, the diffraction intensity peaks for sodium aluminate become stronger, and the rare earth metal now exists as oxides. This shows that the structure of the waste rare earth metal fluorescent powder has been destroyed. Meanwhile, in Figure 6c, where we have a ratio of 2.2:1, the phase structure does not change except for the sodium oxide diffraction peak, which is as a result of the excess sodium hydroxide added. Again, a study on the extraction of rare earth elements from neodymium iron boron magnet scrap by a mixture of aluminium fluoride and sodium fluoride melts was carried out. The steps involved is shown here, similar to the previous ones that we have already discussed. The constitution phases of the reaction products were determined by X-ray diffraction measurements using copper K-alpha radiation. Similar to the other experiments, the X-ray diffraction pattern of the initial magnet scrap is shown in Curve A. Curve B shows the products from the initial fluorine melt. In Curve C, we see the products obtained after the molten fluorides have been deposited on the surface of the granule scrap. And in Curve D, the obtained salts are identified. It was noted, however, that praseodymium fluoride and dysprosium fluorides were not identified because of their low content level in the obtained salts. From these studies, we can see the importance of X-ray diffraction in the research of rare earth metals recycling. By using X-ray diffraction in rare earth metals recycling, we can ascertain the presence of certain target elements or compounds after the recovery process. Also, residual compounds are analyzed to determine the efficiency of the process or method used. Thank you for listening.